We've been working with quadratic equations and mostly we've been solving them lately, but now we're going to see how a quadratic equation like this can apply to a real scenario. So I'm going to have a scenario where an object is thrown through the air and after a certain distance it returns to the ground. That's because we're using this because gravity operates under quadratic conditions. So without adding a lot of context to it, the scenario might look like this. An object is thrown from the roof of a building, it travels forward and upward, and eventually it hits the ground because that's what gravity does. So if you went to your friendly graphing calculator or Desmos and graphed this, you would see that, which in this case literally represents the path, well maybe figuratively, represents the path of the object through the air. So here you see the spot at which it was launched, and eventually it hits its maximum height and returns to the ground. Now if you wanted to find out the location anywhere along the line, then you would go ahead and plug in to this equation. For example, if I was wondering, after it had traveled for 4 feet, how high up in the air is it? What I'm really thinking of is 4 comma what? Because 4 feet represents the distance along the x-axis or the x-coordinate. The y-coordinate is the distance up. So the ordered pair 4 comma I don't know would say after 4 feet of travel I'm at a height of I don't know. Well, how do you know? That's pretty easy because we've been doing this all along. Anytime I want to get a value out of an equation, I plug into the equation to get a value out. So in this case, you could think of it as making a t-chart. And we were interested in 4 feet along, so that's an x value of 4. I plug the 4 into my equation. So I've written the equation up here. But since I'm interested in the distance 4 feet into the flight, I plug in a 4 for my x. I should write an x there. And that means I plug a 4 in for here. I accidentally used t's instead of x's, so let's go ahead and change those. Naughty me. That's an x. That's an x. But that doesn't matter because we're going to plug in a 4 anyway. And when I go through crunching those numbers, I get a 48. That means 4 feet of travel forward left me at a height of 48 feet for the object. And I could do this for all the rest of these. And by the way, you'll notice that eventually on my graph, the object returned to the ground. And I could have verified that because if I plugged in a 12 into my equation, the numbers would eventually work out to a 0. So if I feel like it, I can do this for every moment or every distance along the path, and I would get a bunch of points, in this case 4 comma 48, and I could graph those points. And when I did, I would get the same thing that you got here. But now that we have that graph, we're going to talk a little bit about the anatomy of the graph. We've talked about the anatomy of our quadratic functions as we've been going through this unit. So I'm going to take a look at this and I'm going to think about the x-intercept, the y-intercept, the vertex, the domain, the range, and the axis of symmetry. So here's a list of all those items. We're going to go through and we're going to compare it or answer them based upon this graph and this scenario one by one. So let's start by looking at the vertex. In this case, the vertex of the graph is 5 comma 49. So that's just a point, but it has some actual meaning in the context of the problem. So in this case, we see the actual coordinates of the vertex, but it also has meaning. It means as I've traveled 5 feet forward, the object has now achieved a height of 49 feet. And by the way, that is its maximum height, because in this case, as you look at the vertex, it is a maximum point on the graph. In this scenario, we look at the y-intercept, and it's 0, 24. And as you might guess, this is the launching point of the object, so it is the initial height. And you could say the initial height of the object or of the spot where it is thrown from. Now we're asked for the x-intercept. We just looked at the y-intercept where the graph intersected the y-axis. The object travels through the air. Boom, it hits the ground. This is the x-intercept because this is the point where we hit the x-axis. So in point form, I'd say 12, 0. And as you would probably logically figure out, the object is traveling through the air and boom, it hits the ground. So that x-intercept represents, in context of the scenario, after traveling forward 12 feet, the object hits the ground. Kaboom. The domain represents the x values. So in your brain, you're thinking the x values. And in a scenario, it represents the x values that are reasonable in the scenario. So if I look at this scenario, any x value over here doesn't really count because this object is traveling forward. It didn't go backwards or into the negative x values. So it doesn't make any sense to have any x value to the left of 0, or 0 is my smallest reasonable x value. Then as I travel forward, after 12 feet of distance, the object hits the ground, so it doesn't make sense to have 13, 14, 15, 16, or 17 in the domain because the object is just sitting there on the ground. So that means I can say the domain goes anywhere from 0 to 12, and that's a reasonable domain for this scenario. And using a similar thinking, I can think about the range, which would be the height. Looks like I've got the lowest height or the lowest y value possible of 0, because that's how far it is. Well, that's the ground level. 0 is the smallest y value. It starts at a y value of 24, but it gets even higher than that. It gets all the way up to 49. It never gets higher than 49. So we would say the domain goes from 0 to 49. And finally, we would have the axis of symmetry. And the axis of symmetry always goes through the vertex, and it kind of cuts the graph into a symmetrical part. You can tell that I haven't drawn things very precisely here, but basically the right side of the graph and the left side of the graph would be symmetrical. Now that's cut off a little bit because it doesn't make any sense to have this part of the graph shown, but I'll draw it in there anyway. And so now you can see the right side and the left side are mirror images of each other. This is the axis of symmetry. It's the line that cuts the graph right in two. It goes through the spot x equals 5, especially if I would have drawn this better. So the axis of symmetry is the line x equals 5. There it is. So basically we've taken a quadratic equation, one that you could have solved by factoring, you could have solved it by graphing, you could have used a quadratic formula, but instead of doing that stuff, we used it to represent the path of an object in motion, and we could have gone through t-charts, plugging in, we could have identified the different parts of the anatomy of this graph, all the same things you've done with regular quadratic equations now applied to this type of scenario.